So our next speaker is Professor Adelson. Edward Adelson is a John and Dorothy Adelson Professor of Vision Science at MIT. He has made many contributions to the fields of human vision, machine vision, computer graphics, and neuroscience, and is now developing artificial touch sensors designed to match or exceed the capabilities of human touch. Probably all of you are familiar with the gel site sensor, which comes from his lab. So today he's going to give a talk on the virtues of soft fingers that extract high resolution content.
Thank you. All right, so I am traditionally a vision guy, and when my kids were born, I thought I would be interested in studying the development of their visual system. But what I found was that the most interesting thing was the way they used touch, constantly using their fingers, their lips, to discover the world. So I became inspired to understand touch, and that's how I ended up doing this work on touch sensing. One interesting thing is that when people think about touch, they tend to think about force. And for example, here's a well-known chapter on force and tactile sensing. And it makes sense because what happens when you touch something is it exerts some distribution of forces on your finger, and that's important to know. But as we've been working on things, I've come to understand the importance of geometry in addition to, or even beyond force. So here are some arguments for why you shouldn't care so much about force. So suppose that you've grasped some object in a stable way, and you squeeze harder or you squeeze less hard, it doesn't matter, it's still stable. Or suppose you're grasping something where you're relying on friction, and you squeeze harder or a little bit less hard, again, it doesn't matter because you're not moving the friction cones around, and again, the geometry is what's really important here, rather than the force. And you might say, well, what about I've got some flimsy object and I don't want to squeeze it too hard because it'll get crushed. Well, if it's something like this plastic cup here, you're going to notice that it's distorting, that is, that its geometry is changing, and that's going to be your signal that you're squeezing too hard. So many times, geometry is really the issue. And there is a long history of sensing geometry, and one way of doing that is by putting a camera inside a finger, which is what we do, but here's an earlier version of that idea from Brockett's lab. And they've got a finger that's got some fluid in it, it's got a membrane with dots on it, there's a camera inside, and they measure the distortion of the dots. And down below, you can see they can distinguish the case of being touched by 1 point or being touched by 2 points. So it has a certain amount of resolution, although not a great deal. So what we do, which we call gel site, is, the idea is shown here. You've got a chunk of clear elastomer, and it's covered with a reflective membrane. In this case, it's basically paint made with some silvery stuff. You press an Oreo against it. Look from the other side. You can see the exact shape of the Oreo by the shading signal. Now, if you know anything about computer vision, you know interpreting a single shaded image is actually difficult. But if you have 3 shaded images with shading in different colors coming from different directions, that turns out to be easy. So that's what we do. We arrange to shade this object in 3 directions with 3 colors, and then using standard techniques, we can extract the 3D shape. And it can be extracted at extremely high resolution. In fact, insanely high resolution. And so even though this project started out as with an interest in understanding touch, human touch and robot touch. We ended up starting a company that sells devices for measuring surface detail. We can measure 3D surfaces with a resolution of a couple of microns in X and Y, or a tenth of a micron in Z. And the advantage over other systems, optical systems, is that we don't care about the optical properties because we're covering it up with this paint. Anyway, if you want to buy a very high resolution, yes?
Which, in the upper right, are those real or artifact?
Those little blips,
The little blips, yeah.
those are real. They might be dust, they might be dings. There's always garbage in the world. Sometimes, I will admit, sometimes we have artifacts, sometimes we have garbage that got built into the sensor, but I think those ones are real. Okay, here's a more recent, version of the robot sensor that we're working on. For robots, you don't need such high resolution, but you do want it to be compact. So this is a compact, medium resolution device. It's high enough resolution that you can resolve the details on a corrugated potato chip. And that's what I'll be talking about, the sort of information you can get from a device like that. The resolution is still significantly higher than that of the human finger, at least in terms of 2-point resolution, and maybe higher than you need for most tasks. Anyway, when we first started working on this, we thought, okay, we're getting geometry, that's our natural language, and we should convert it into force. We'll have to do some inverse thing or have to develop some heuristics in order to get force. But then we started working with Rob Platt, who said, well, many times really what I want is geometry. And so he explained to us the virtues of geometry. And for example, if you've got a robot equipped with one of these sensors and it grasps a USB cable, you can feel the embossed USB logo. If it's felt it before, if it's been trained so it knows these geometric significance, then once it feels that, it knows exactly where it is with respect to its finger, it knows where its finger is with respect to its arm, knows where its arm is with respect to the world. So now it has an absolute measurement of the pose of that cable, and therefore can plan a trajectory to plug it in. And here's a, should go back. So we did this with Rob, with the Baxter, and the demo, I have to say, was disappointing, not because of our sensor, but because of the robot going like this, and being distinctly unimpressive, I'm afraid. So we recently started redoing this demo with a UR5. Which means we just have a better robot and it gives a nicer demo, except it's not doing anything. It thinks it's playing a video, but it's not.
Your hardware accelerator is probably sending it to your laptop. If you mirror screens or turn off the laptop screen.
Let's see, the laptop is not showing it either. Well, I'm disappointed. I may not be able to show you any videos.
Invite us to your lab and we'll watch it there.
Okay, anyway, you can imagine what it does. It grabs, a person hands the robot the USB cable. It's at some random position. The robot figures out the right position and sticks it beautifully, smoothly into the USB port. And let's see if we have any luck here.
do you have separate video files?
I do. I have these files elsewhere, but I can't put my finger on them at the moment. All right, I'm going to tell you what you would see if this was working. So what happens here, the robot grabs the USB cable. Actually, I'll show you. Let's see if my other thing works. All right, so here you're looking actually at a live demo of this device. Is it okay if I grab the USB demo from here? Whose is this? The USB cable?
Oh, yeah.
All right, so there's the USB cable. What's on the left is that's the raw video in the back, and then there's the shear displacement information in the yellow arrows. So anyway, what you see when the robot grabs it is, first of all, you see this wonderful detail. Secondly, you see all kinds of stuff you didn't expect to see, like it grabs it, and then it kind of settles into place. It doesn't stand exactly the same place. And then when you insert it, there's shear, and you can see the shear shooting up, and then you pull it out, the shear goes the other way. So there's all kinds of wonderful stuff to be seen. And as long as I'm here in live demo mode, I'll show you a few other things. So I can touch this with my finger, and as you see, as I rotate it in contact, you can see the torque of those arrows. Here's my hair, picks up wonderful detail. If I slide it across my hair, you'll see the motion of the hair, and as well as the shear with those arrows. And it's pretty obvious when you look at this that it's going to be easy not just to measure shear, but also to measure slip, because slip, again, that's inherently a geometric measurement that says the motion of the membrane is different than the motion of the thing sliding over the membrane, and that's easy for us to measure, so we can measure slip. Let's get back here. And a more elegant, powerful conceptualization of what we can do here was provided by Russ Tedrake's lab, where you can view this as a problem in sensor fusion. Think of this finger, since it's giving you this high-resolution 3D, think of it as a little baby Kinect that's on your finger, giving you an RG, well, it's not giving you RGB, it's giving you just a depth signal, instead of point clouds for depth. And you've got other sources of depth, right? You've got some connects in the room, you've got some prior models of the room, and so if you do things right, you can bring all this information together in some very nice way and use it to do tasks like, in this case, manipulating a small screwdriver. Now, one of the points that's sometimes not obvious is that people think that soft fingers are inherently going to give you some uncertainty about position. It's plausible, right? On the left is suppose you've got a little capacitive array there, and you cover it with some chunk of elastomer to make it soft, and you push on it with that green thing, well, you're going to lose resolution. Or next to that, you've got some chunk of resistive elastomer, and you press on it. Again, that's going to inherently be low resolution. But on the right, if you've got a clear chunk of clear elastomer with a membrane over it and a camera, then the camera can see everything that's happening at the membrane perfectly. And so there's no loss of resolution. And the other nice thing is those other techniques have this wiring problem. You have to get all the wires out of there. And a camera has already figured out how to do that and just give you a single cable. So there's nice things about these camera-based systems. The thing that's not so nice about a camera-based system is you need to find room for the camera, you need space for it to do its thing, to see stuff. So either you have to have lots of little cameras, or you have to have a large area for a camera. So there are some disadvantages. All right, so here's some more demos that you've actually just seen. That's Wenjen on the bottom there, who's responsible for a lot of this work. And Srinivasan, who's a haptics guy who's been instrumental in a lot of the gel site work. Okay, and here again, well, you just saw that demo, so I don't need to do it. This probably is not going to work, but let's just give it a try. All right, well, you can imagine what's going to happen here. This robot's going to pick up a can of Red Bull. And it's not going to slip because it can measure slip. So what it can do is it squeezes hard enough to feel it's touching, it lifts up, it senses whether it needs to squeeze harder or not, and it lifts the thing up without slipping. The problem, of course, is suppose you just told it squeeze really hard to make sure it doesn't slip, then you would crush things. For example, suppose you had a little leaf like this, a floppy little plant leaf, and you wanted to hold it this way. Well, we can do that too because it's sensitive enough that it'll feel it as soon as the leaf touches. It can feel that the edge of the leaf. And so, without changing parameters, without fiddling, we can pick up a leaf or a can of soda or a can of Red Bull. All right, so there's lots of geometry that's interesting that you can measure with a tactile sensor like this. So obviously the shape, in many cases you can identify the object by that information. You can get its pose, shear and slip as we discussed, and other things like if I'm touching an edge, I want to know how sharp it is, I want to know what orientation it's at, and I might also want to know compliance. Well, I have not talked about compliance, that is how hard or soft something is. And it's not obvious how that would be a geometric measurement. In fact, inherently it doesn't seem like it. So what does it mean? Well, it's sort of like, right, you're measuring something like the spring constant of this material. You've got this rubber or whatever it is. And how do you do that? Well, you press, you measure how much force it takes in order to deform it a certain amount. So that's what you think of as being hardness or softness. Or if I've got let's say I've got an avocado, I want to know how hard the avocado is. I squeeze it a little bit, I see how much I have to deform it in order to, how much it deforms in response to force. That's what people think they do with avocados. But really what people do with avocados is mostly you're responding to the deformation of the fingertip surface. You're not trying to measure all of these angles with great precision. And in fact, you can take an avocado, close your eyes, put your finger on the table so you can't move it, have somebody else put an avocado on your finger, and you can tell whether it's ripe or not by how soft it is. So that's an interesting thing to try to replicate. What's really challenging about an avocado is it's a funny shape. Not only is it round, but it's bumpy. And I will say, we don't know for sure that we can do avocados accurately, but we can do lots of shapes, and we think we can do avocados. So then here's the goal. Can we use this kind of sensing to enable a robot to go shopping and buy ripe tomatoes, where ripe means it feels ripe? And previously, when people have measured hardness or softness, they've used rather constrained conditions, like you have to have it has to be a flat slab, you have to be able to measure force accurately. So we want to be able to do it in a much more general situation. Again, here I can't show you this. Oh, actually, I have demo materials I could use here. Well, I'll just do it with my hand. Okay. Do I have some like nice hardware? Is it working?
No, I meant be a real.
Oh, right, I've got to switch. So you can see it. All right, well, the basic thing is this. When you push on something, if it's soft, let me push on this piece of my palm, it squishes, it changes shape as you push. As you push harder, it changes shape more and more. And if you have something that's hard, like, say, my fingernail, it doesn't change shape. No matter how hard you push it, it stays the same shape. So it is the changing shape as you push harder. That's the cue that we're going to use. And that means we're not just looking at a single image, we're looking at a video sequence. So we're going to push on a fruit, and or a synthetic object, and as we push, we're going to see how much it changes. Well, it turns out to do this in a, say, mathematically correct way, to figure out exactly how to transform the signal into an estimate of hardness is beyond our capabilities. So machine learning comes to the rescue, in particular deep learning. From our point of view, deep learning has picked up all this momentum just at the right time because we've got masses of information coming out of the sensor, and we don't know how to interpret it. But we can use deep learning if we've got a way of training it. And in this case, that meant that WinGen made a whole lot of objects, 300 objects of different shapes with known hardness by using different kinds of rubber. And then down below is showing some still pictures of what happens when you touch it. So you go and you touch all these objects. You've got the ground truth on the hardness of each object. We intentionally touch them in a kind of uncontrolled way, touch them from different angles, different positions, different orientations, and they're all different shapes, so that we can try to learn invariant measurements for hardness, the material property. And the answer is, and here's the, for me this is just black box. I know this is the currently correct way to do things in deep learning because my students tell me it is. Anyway, CNN, that's your classic neural net with convolutional neural net. LSTM is a kind of neural net appropriate for sequences, for video sequences. And the results are here. I would say they're pretty good. There's the ground truth, Shor double zero scale. Here's the estimate. These are familiar shapes, but made of rubbers that it's never felt before. So you never have the exact, you're never measuring the exact same stimulus you've measured before. If we do it with unfamiliar shapes that you've never actually touched before, then we do somewhat less well, but still pretty well. And can we do avocados? Well, we don't have ground truth on avocados, but we know that we can order avocados in the same ordering that human subjects do. All right, I don't have time, I think, to do more, but just mention, because we're getting such rich data, not just rich spatial data, but spatiotemporal data, in this video sequence, we can use it to recognize fabrics. So if you're sorting your family's clothes and you've previously learned which kind of clothes need to be washed in hot or cold water, clearly we cannot do color information, so we can't sort the whites from the colors. But in terms of like silk versus wool, that sort of thing, easy to do. Let me just summarize. So soft fingers with internal cameras can measure contact surface geometry with great precision. You could infer force, and you may want to, but you may not need to in many cases. GelSight's one particular way of getting really high resolution. And it provides data that can be used to support various manipulation tasks. Among other wonderful things we can measure is shared slip with great accuracy. And you can also infer other properties, for example, hardness, that are non-obvious. And I think now and in the future, we are finding deep learning to be a really valuable tool for us to transform the rich data that we're getting out of this sensor into something that can be meaningfully used in tasks. Thank you.
Before we begin the question session, I have a small announcement. Our next thing is the poster spotlight. So for the poster spotlight talks, I emailed you last night with an order. So during the question and answer, if you could just line up here. All the slides are arranged in that order in this cup. That would be great. Yeah. Questions for Professor?
Any questions?
Have you actually done the laundry thing yet?
Oh, have we actually gone to somebody's house and washed their laundry?
Or Ash?
No, but we have a basket of a closet full of laundry in the lab, and yes, we can learn to recognize which item is which. This is what we've done is really pretty simple because we're assuming a household has a finite number of articles of clothing. We just have to recognize them. So it's not too difficult to do.
I'm going to argue that we really should all be doing computer vision, and yet you somehow rejected computer vision. Being able, for example, to orient to the USB cable before you touch it is very valuable. So what's the deal? Why have you left your roots behind? They're so useful.
Well, so I'll give you an honest answer, which is that these days, computer vision, there are so many really smart people doing such amazing stuff in computer vision, especially when you combine it with machine learning, that I feel like I don't have as much to contribute as I used to. I mean,
so
people are just
they're
doing
moving into Sleepy Hollow.
people are
That's straight.
So people are doing great stuff, and people are doing great stuff in touch, of course. And the talk we heard before is an example of great stuff. But I have something, basically, I have something to offer. So I think that this is fun and interesting. And I have to say, I'm learning a lot. I started out as a vision chauvinist, thinking all other senses were inferior to vision. And maybe they were just like vision, but sort of bad versions of vision. And I've come to appreciate touch is just an amazing sense that's completely different than vision, and it's integrated into all this stuff with action, and so it's a great place to be. Yeah.
So I completely accept the argument that geometry is very important and overlooked, and it's very valuable, and shear forces, you had some amazing results. But still, can you infer normal force? I guess depth of indentation somehow as a proxy for it? Do you have a method for that?
Well, we have worked on it, but the brute force thing to do is you build a finite element model of your sensor, and then you've got an inverse problem where you figure out, okay, what would the forces be in order for that shape to exist. So in principle, you can do that. That's going to be slow, so you're probably going to want to convert it into some heuristics that will be faster. And we played around with stuff, but we haven't really gotten seriously into it because we've been distracted, let's say, by all the interesting stuff you can do with geometry, which is much easier for us to measure.
The expansion of the marker field gives you a crude measure of normal force.
Indeed, right. As you push on it, it spreads out, and you get a rough estimate of force.
Thank you, Professor Adelson.